All right, so in this example, we'll cover doing an improper integral where we see an infinity hanging out as one of the integration bounds. In particular, looking closely to this integral from -3 to infinity, that upper bound of infinity is what's causing kind of the little hiccup so far in terms of what we've done before in this course. So we're looking at the improper integral from -3 to infinity of e to the minus x. So to give you a sense and reminder of what we're doing, we are still doing a definite integral, which suggests we are still computing the area under some curve. It's just that the curve we're looking at right now is a curve that extends all the way to positive infinity. So our function looks something along the lines of a decaying exponential, something like this. And what we're wondering is, even though this is going all the way to plus infinity, we're wondering if that area underneath the curve, say -3, is some finite number. So again, this is a kind of interesting point because we're saying, even though this integral is extending all the way to positive infinity, it just keeps on going forever. We're wondering whether or not the area underneath such a curve could be finite. All right, so without further ado, let's get right into it. And the first thing that I remember I said was, what saves us for improper integrals is introducing limits. So we're going to introduce a limit to basically help us get away from thinking about this as an upper bound of infinity. And literally what I mean by that is, we'll take a limit and replace that infinity as a limit as some variable, say, I don't know, let's use c, approaches infinity. So when we rewrite this integral, we're really just thinking of the integral from -3 to 3 of our original integrand. So the only thing that really changed here was swapping that infinity for a c, but taking the limit as c goes to positive infinity. And now that we've introduced that limit, what we're really saying in terms of this definite integral now is, we're thinking of this definite integral as having a fixed first end at -3 and a fixed end at c. It just so happens at the very end of the problem, we're going to keep kicking c larger and larger until it gets to infinity through that limit. But once we've introduced that limit, we can just proceed with the problem as we would any other definite integral. We just get to lag around that limit as c goes to infinity along for the ride. So the next thing we get to do is just compute the antiderivative of e to the minus x. And the antiderivative of e to the minus x is minus e to the minus x. And we're going to evaluate that at the lower bound of -3 and the upper bound of c. So let's go ahead and plug in those bounds. So plugging in the top bound, subtracting off, evaluating that at the lower bound. So far, we've sort of just ignored that limit and just treated c as though it's any other number, which is really the spirit that we want to take here. It's not until the very end, after we've inserted the upper bound, subtracting that antiderivative at the lower bound off of it, is where we really do the limit. I'm just going to take this one step further, just do a little bit of algebra and arithmetic to clean this up a bit. So what this limit looks like as c goes to infinity is of minus 1 over e to the c. We have a minus, oops, there should be another minus there. I forgot this minus before. This minus should be there. A minus minus will give us a plus. E to the minus minus 3, which is just an e cubed. So really, the function in which we're wondering what happens as c goes to infinity is the function of minus 1 over e to the c plus e cubed. And now if you're just a little rusty with your exponential rules. Remember, if we have something that is e to the minus x, that's the same thing as 1 over e to the x. And that's the exact thing that we did to get that 1 over e to the c in the denominator. So if we take this limit, basically what happens as c goes to infinity, that denominator of the 1 over e to the c term gets really, really large. So 1 over a really, really large number is just 0. So this limit goes to 0. And at the end of the day, the total area under the curve happens to be e cubed. And since e cubed is a finite number, we actually get to call this something special. We call this case convergent, because the definite integral that gave us the improper integral just became a finite number, as in a number that is not plus or minus infinity. So it's convergent.